Hi guys, it's Dr. Bay, and here's Bugsy, and today we're going to go over carboxylic acid derivatives, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Carboxylic acids are compounds that contain a COOH group as shown here in blue. Now, if we replace the OH group with a heteroatom like chlorine, oxygen, or nitrogen, then we get a carboxylic acid derivative. The four most common types of carboxylic acid derivatives are an acid halide, acid anhydride, ester, and amide. And we can rank the relative order of reactivity amongst these four carboxylic acid derivatives. Since chlorine is an electronegative atom, it withdraws electron density away from the carbonyl, making the carbon of the carbonyl even more electrophilic than that of the other three derivatives. Now, the main difference between carboxylic acid derivatives and aldehydes or ketones is that the carboxylic acid derivative contains a heteroatom labeled as Z that can function as a good leaving group. Whereas ketones and aldehydes do not have a good leaving group because remember that carbons and hydrogens are not able to break off of a molecule and be stable on its own. So, because carboxylic acid derivatives contain a heteroatom that is a good leaving group, there is a whole class of reactions called nucleophilic acyl substitution, where a nucleophile attacks the carbon of a carboxylic acid derivative while the nucleophile replaces the leaving group. The general mechanism of nucleophilic acyl substitution consists of two main steps. First, the carbonyl group is attacked by a nucleophile and forms a negatively charged tetrahedral intermediate. Then one of the lone pairs on O- comes back down to reform the carbonyl pi bond, while a good leaving group, letter Z, breaks off. This forms a new carbonyl product. Now let's take a look at an example where this carboxylic acid derivative, specifically an acyl chloride, is reacting with NaOMe. Recall that we can rewrite NaOMe as Na plus and OMe minus, where OMe minus can act as a strong nucleophile. So OMe minus attacks the carbon of the carbonyl while the pi bond breaks to form a new lone pair on oxygen. This forms the following negatively charged intermediate. Then a lone pair on O- comes back down to reform the carbonyl and Cl leaves. So remember that C- should never act as a leaving group, so don't kick off the phenyl ring instead of the chloro group in this particular example. Then this forms our final product, which is an ester. Now the mechanism of nucleophilic acyl substitutions is actually dependent on the type of condition the reaction is under. If the reaction is under acidic conditions, you want to make sure that your intermediates are positively charged in order to stay consistent with the particular reaction condition. So let's take a look at this following example. An ester is reacting with sulfuric acid and water. The first step is for oxygen of the carbonyl to get protonated by H2SO4 to form a positively charged intermediate. Then water attacks the carbon of the carbonyl and the carbonyl pi bond breaks to form a new lone pair on oxygen. Since the entire water molecule is attaching to the molecule, it has too many hydrogen atoms connected to the positively charged oxygen. So another mole of water comes in to deprotonate the extra hydrogen to get the following intermediate. Then, because we want the ethoxy group to be our leaving group, we then protonate the oxygen atom using the newly formed H3O plus to make a better leaving group. Then one of the lone pairs from OH comes down to reform the pi bond, kicking off the leaving group. Then in the final step, we just need to deprotonate the extra hydrogen atom using water to form our carboxylic acid final product. Now let's compare the mechanism to a reaction under basic conditions. The same ester from the last example is now reacting with ammonia or NH3, which is a base. The first step is that the nucleophile NH3 attacks the carbon of the carbonyl, and then the pi bond breaks to form O-. Then a proton transfer occurs to move one of the hydrogens onto the ethoxy group to form a better leaving group. Then one of the lone pairs from O- comes back down to reform the pi bond of the carbonyl, and the leaving group breaks off. This forms the amide final product. So remember that acid chlorides can be made from a carboxylic acid and using thionyl chloride or SOCl2. The mechanism of this formation is in two parts, where one of the lone pairs from the alcohol-oxygen atom form a new carbonyl pi bond, while the existing carbonyl pi bond acts as a nucleophile to attack the sulfur atom of SOCl2. This forms the following zwitterion intermediate. Then one of the lone pairs from O- comes down to form a double bond between O and S while kicking off one of the chloride atoms. Then the Cl- that just broke off comes back and deprotonates the extra hydrogen atom to form a neutral intermediate. Note that the group highlighted in blue is a good leaving group. Now in part 2 of the mechanism, we're actually going to rewrite the molecule so the carbonyl is right side up. Then Cl- comes in and attacks the carbon of the carbonyl, and the pi bond breaks to form a new lone pair on oxygen. Then one of the lone pairs in O- reforms the pi bond, the carbon-oxygen bond breaks to form a new lone pair on oxygen, and the good leaving group leaves. This forms the acyl chloride product, and the SOCl- byproduct actually breaks down even further to decompose into SO2 gas as well as Cl-. Now let's get into a bunch of reactions that involve acid chlorides. Hydrolysis of an acid chloride forms a carboxylic acid using water. The mechanism starts off with water acting as a nucleophile to attack the carbon of the carbonyl, and the pi bond breaks. This forms the following intermediate. One of the lone pairs from O- comes back down and kicks off the Cl. Then in the final step, another mole of water deprotonates the extra hydrogen atom to form a neutral carboxylic acid product. Alcoholysis of an acid chloride forms an ester using an alcohol and pyridine. The mechanism is actually analogous to the last reaction we just looked at, hydrolysis of an acid chloride. Now here's another way that alcoholysis of an acid chloride can be written. The alcohol can be shown as the starting molecule, while the acid chloride and pyridine are the reagents, but you would get the same ester product regardless of which method is used to write the reaction. Note that this reaction is sensitive to steric effects. Primary alcohols are more reactive than secondary alcohols. In the following example, the starting molecule contains both a secondary alcohol to the left and a primary alcohol to the right. When this molecule reacts with an acid chloride, it will selectively attack only the primary alcohol, which is less sterically hindered, in order to form an ester, while the secondary alcohol on the left actually remains untouched. Aminolysis of an acid chloride forms an amide, and each of these mechanisms are analogous to hydrolysis of an acid chloride as well. This reaction can work with ammonia or NH3 to form the following amide. It could also work with primary amines to form the following monosubstituted amide. And it could even work with secondary amines to form the following disubstituted amide. So the product will just be dependent on the type of amine that is used. And lastly, acid chlorides can be reduced using any of these three methods. To reduce an acid chloride to a primary alcohol, you could use an excess amount of LiAlH4 in the first step, followed by water in the second step. To reduce an acid chloride to an aldehyde, you could use a bulkier lithium reagent like lithium tri-tert butoxy aluminum hydride to form an aldehyde. And last but not least, if you want to reduce an acid chloride to an alcohol while increasing carbon count because it is an organometallic reagent, you could use an excess amount of an organometallic reagent in the first step, followed by a water workup to form the following alcohol. So in summary, nucleophilic acyl substitution reactions are where a nucleophile attacks a carboxylic acid derivative and the nucleophile replaces the leaving group. There are a bunch of different reactions with acid chlorides, such as hydrolysis, alcoholysis, aminolysis, and a variety of reduction reactions.
Organic.